Welcome back everyone. This week I'm going to show you how to do semantic analysis with Uranium, and it's going to be part 1 because there's quite a lot to talk about. So we're currently talking about semantic analysis, which is what you do after you get a tree from parsing. And using that tree, you do things like type checking, name resolution, all kinds of checks really. The last video was on the in-liminal type system. We saw that the system is made of inference rules with premises and conclusion, potentially multiple of them. We use the type system to generate typing judgments, and from a ground set of facts, we chain the inference rules together. So we plug the conclusion of some rules into the premises of other rules, and that lets us derive more and more type judgments until we can type everything that we need. This time, I'm talking about Uranium. So Uranium is a library written in Java, and it's made to facilitate semantic analysis. It's inspired by formal type system, like we saw last video, attribute grammars, that's something I will explain today, and reactive programming. So the goal of Uranium is the declarative specification of dependencies, and we'll do this via rules. What do I mean by specification of dependencies? For instance, I want to say the type of a function call depends on the type signature of the function and the type of each of the arguments. So that's a dependency between the type of the function and the type of the declaration of the function in the arguments. It's declarative because we don't want to think too hard about ordering. So for instance, I don't want to think about the definition of the function being after the call site. If it's defined below it, I might not have seen it yet. So I need to think about how I ordered this thing, and I don't want to do that. So Uranium lets you avoid thinking about that, at least thinking about that too much. However, we have to be explicit about the computation of the attributes and all the various checks that we want to do. So for instance, we need to write some code that checks that indeed the arguments match the type signature of the function. We'll still need to walk the tree once, and the reason we need to do that is that we need to create these declarative rules. So I said I'd say something about attribute grammars because they're very similar in spirit to Uranium, and they're a much more established concept. So the goal of attribute grammars is to calculate attributes on AST nodes. So for instance, a typing judgment for more type system could be seen as the type attribute of a node that represents an expression. There are two main kinds of attributes, synthesized attributes, and so this when you compute an attribute using the value of attributes of the node's children. Okay, so you go from the bottom of the tree towards the top of the tree. The other one is inherited attributes. That's when you compute the value of an attribute by using the value of the attributes of the parent. So you go from the top of the tree towards the bottom of the tree. You can also chain these two together. So if you have a tree and a node in the tree as a sibling, then you can use a synthesized attribute to transfer the value of a node to the parent, and then an inherited attribute to transfer this value from the parent to the sibling. There are more types of attributes that have been proposed in practice, for instance, circular attributes, which allow to do fixed point computation. So a simple example of that is reachability analysis. So you want to know where in your program a function can be called for, directly or indirectly. So you do a reachability graph, it's called. The problem is you have recursion. So if you have recursion, potentially this graph has loops. And this is a computation that may not necessarily finish, but using circular attributes takes care of that. So there's a whole lot of literature about attribute grammars. I don't want to enter into the details. Just know that it's quite researched. Attribute grammars straddles theory and practice. It's actually a very academic system. In practice, there are frameworks that you can use to do this, and they're using domain-specific languages, either internal, so that means the DSL is written in a language. For instance, Kiyama, that's a Scala DSL, or external DSL, so that means there's extra syntax. So there's just add that's written in Java, but they add more syntax to deal with the attribute grammars. I think attribute grammar is a terrible name. It was originally called like that because you originally had to write the rules in an actual grammar. That's a terrible idea. In practice, you really want to write your rules in terms of AST nodes. If you write it in a grammar, first of all, you're polluting the grammar, it's unreadable. Second of all, it weds you to the syntax tree of the grammar. not the abstract syntax tree, but the syntax tree that follows the structure of the grammar. The whole grammar would be an attribute grammar because it has these annotations here. So there's an example from Wikipedia. And in this example, you have an expression grammar. And these annotations tell you how to compute the value of the expression. So in this case, the attribute grammar is used as a way to do an interpreter, which is not really what you should be using it for. That's not a good use case. Anyhow, this shows synthesized attributes. So for instance, you want to know the value of x per 1, which is defined as x per 2 plus term. Well, that value is the value of x per 2 plus the value of term. Okay, so it's a synthesized attribute because using those attributes, which are the attributes of the children, you can compute the attributes of the parent. And how do you get those? Well, you just use the rule that's matched, like for term, the rule is there, and x per 2, that's just recursive. By the way, attribute grammars were invented by Donald Knuth, which is also the inventor of LR parsing. I put this picture on the LR parsing slides, but I forgot to mention it. So this gentleman gave us LR attribute grammars, but also LaTeX, the document typesetting system, and he's also writing a very famous series of books called The Art of Computer Science, which he's been writing for a long time now. So this is not quite as famous as his other inventions, but as you can see, it's quite old and well established, so I would be remiss not to mention it. So let's focus on Uranium in particular. So the goal is to compute attributes, and there's two notions here I want to untangle. There's the attribute itself, which is a pair of an AST node in a string, which is the name of the attribute. And then there's the attribute value, and that's the value assigned to that. So for instance, you could have an expression node with a string that is, say, type, and the value of that would be the type of the expression, so it could be int, float, string, or something like that. We compute these attributes by using rules. Okay, so what's a rule? Well, a rule has one or more dependency attributes. That's what it needs to do the computation. It has one or more exported attributes. That's what is being computed. We need to write some code that can access the dependency values and will override the exported attribute values. This code will be automatically called when all dependency values are available, and that's the job of the reactor. So without further ado, we're going to go into the code. I've wrote a small language and I've wrote semantic analysis for it, and I'm going to write you through the whole code of semantic analysis for that language. The reason I'm doing it like this is that I said multiple times that semantic analysis is an engineering challenge. And what I mean by that really, it's that it's implicit knowledge. If you had asked me to go from zero and write slides on semantic analysis, to be honest, I don't really know what I would have said. So instead, I went through the exercise of writing the semantic analysis for a language. And of course, it came to me that there are things that there's a certain way to do it that works well. Even if you don't know the way, if you spend enough time trying, you will sort of come up with the way yourself. But of course, it's always easier to be shown. So I'm going to show you. So there's a lot to say, and before we can start, I need to give you a lot of context on what we'll do. So first of all, I will show you my language. And so I have this file here, kitchen sink. It shows all the syntactic feature in the language. So my language is a simple statically typed language. Think of it as Java-like without the object orientation. So as you can see, we have a function. Here's a function here. And one peculiarity is that we can nest function into functions. That's something you can do in Java, for instance. And even more peculiar, the scopes inside the functions work just like scopes in classes in Java. So you can actually call a function even if it's defined after. So that's one of the little fantasies in my language. Otherwise, it should be pretty simple. Here we have a parameter, a return type of the function. You have variables, while loop, if statement, which both of these can have parentheses around that or not. Let's see, what else do we have? We can work with arrays. We can print things. We have structures. So for those of you that are doing the project, my language satisfies all the requirements that we asked you, except it does not have built-in maps, but it has built-in structures, which is actually harder to implement. So it should be equivalent. You can see that we can use the structures here, field access. This is a bit cute. So the way I construct structures is that I make a constructor, and I make a constructor by appending the $sign before the name of the structure. So the reason I do that is basically that in my language I can also pass types around. Currently it's useless, so you can pass types around as values, but you can do nothing with them. But because I had this feature, I could not use the name of the structure as the name of the constructor, because I can also pass functions around, right? And I want to be able to pass the constructor around as well. And so there would have been a clash between a spare the name of the constructor or a spare the name of the type. And so to disambiguate, I have this notation where the constructor is always preceded by a $. Oops. And oh, this here is interesting. This tests that it's able to infer the type of the empty array. Okay, so here we have a string array and we assign the empty array. Here we have an int array and we assign the empty array. The problem is, when you see an empty array, you do not know which kind of array it is. Okay, so you need to infer that from the context, which in this case is the declaration here. Okay, so that should give you an idea. Now let's go into some supporting code. So here's my AST. I actually counted, there are 33 classes there. Fairly standard number. We have the type hierarchy. So the root of type hierarchy is this type class, and each type will have a name, and it will be either a primitive type, so those are Boolean, floats, and integers, or reference types, anything else. So you see this is very simple, it's a primitive type, it's called bool. We have function types, and function types have the type of the parameters and the return type. We have array types, which are basically wrappers around the type of the array, the type of the component on the array, sorry. String type, that's for the, basically I reuse the Java string type in the interpreter. Struct types, those are introduced when I declare a structure. So for instance here, this introduces a struct type called pair. And this has the declaration node for the structure. Void type is interesting. So that's the type of function that do not have a return type. So those are void function in Java. Having this type helps me in the implementation of the semantic analysis. And I also have a null type. So null is not very fashionable, but it's my language and I do what I want. And the null type is what is called a bottom type, because it can be assigned to every single type that is a reference type. So it can be assigned to primitive types, but it can be assigned to any reference type. I think that's it for the types. And I need to show you scopes. So what is a scope? It is introduced by a node, and it has a parent. So that is the innermost lexically enclosing scope, the thing around it. And the scopes are chained this way. A scope is a set of declaration from string to the node that creates a declaration. You can look up in a scope, and this lookup is recursive, so it first look up in this scope, and then it will look up in the parent scope. The return value for that is a declaration context, and that simply holds the scope where the thing was found and the declaration node. And well, you can also add things in the scope with declare. So something that's interesting is the root scope here, which is the main scope of the program, and that's where I define all the things that are available to the user by default. Okay, so you have all the basic types, boolean, in, float, string, void. You also have some special values, and actually those are encoded as variables, so true, false, and no. And funnily enough, because they are encoded as variables, you can actually reassign them. This is a terrible idea, but you could, in the current state of the implementation, assign true to false. I'll probably change that later, but currently I haven't. And there's a print function. These values here, they're from an enum declaration kind. That's not very important. Something to note. You have seen that when we do a lookup, we return a node. These things are not defined in the AST. They're not defined in source code. They're supplied by default. Yet we still need a node. And so what I've done here, my solution to that issue, was to create a fake node. And that's this syntactic declaration node. And so it just has a kind in the name. Again, this is an implementation detail, but it shows you one of the challenges that I faced. Okay, so that's it for the support code. And now we will go into the main thing. So it's a pretty big class. It has almost 1,000 lines of code, including a bunch of comments. And actually, it starts with a very big comment that explains everything I do in this class. And I highly suggest that you do the same thing, otherwise you're going to be lost. This explains what needs to be checked and how it needs to work, what needs to be done for everything to work correctly. You should try to be organized like this. It will really help you. So I'm going to read through the comments. It will give you an overview of everything you will see in the semantic analysis. This is going to be split between multiple videos because there's a lot to cover. And today I think we're just going to have a look at mostly typing expressions. So the semantic analysis class holds the logic implementing semantic analysis for language, including typing language solution. So it gives you the entry point to this class, and I will explain that. So big principle, the things we need to do. Every declaration node must have its type attribute set to an instance of type. So we've seen type, right? Which is the type of the value declared. For struct declaration, this is always type. That's because, as I said, you can pass types in my language. So we consider that a structure declares a type literal. So let's take this again. So this basically declares a value pair that you can then use as a value. So you could do this, for instance, this is valid. So let me show you the different kinds of declaration that we have. We have field declaration, fun declarations, functions, parameters, structure declaration, the synthetic one, that's the fake one, so that doesn't really count, and variables. So the type of variable is going to be, well, obviously the type that you specify for the variable. Type of the function is going to be a function type that we've seen here. We've talked about structures, and a field declaration is essentially a variable declaration, but inside a structure like this. This is a variable declaration. Okay, so we need for each declaration to compute its type. For structures, we also need to set their declared attribute to an instance of the type being declared. So for structures, the type attribute is always type because we declare a type. But the structure statement also introduces a type, which is pair. Okay, so pair is a type, and I can do something like this, for instance. So this is also a type, and this will be in the declared attribute. Don't worry, you don't have to remember all of this. We'll go. I will remember it to you as we go, but I just want to give you an overview of everything that needs to be done. So every expression node needs to have its type attribute similarly set, so every expression needs to be typed, basically. Every reference node must have its decal attribute set to declaration it references, and its scope attribute set to scope in which the declaration it references lives. And I explained that this speeds up the lookup in the interpreter. So what's a reference? A reference is whenever you use a variable or whenever you call a function. Okay, so this is a reference. Print is a reference. Math is a reference. Validate5 is a reference. Okay, and so we need to determine that validate5 is defined there, and we need to set the decal attribute to the node for this. Okay, and we also need to set the scope attribute to the scope where it's found, and this is just to speed up the interpreter. Don't worry if when you start doing semantic analysis you don't think about the interpreter just yet. It's fine. You can go back, and sometimes you will have to modify a few things in the semantic analysis to make it easier on yourself later. But generally, you won't have to change a lot. Okay. So similarly, the variable declaration node should have the scope attribute set to the scope in which they appear. I actually don't remember why this is necessary. We'll figure it out. All statements introducing a new scope must have their scope attribute set to the corresponding scope. And I specify that these statements that introduce scopes are a root node, block node, and a function declaration node. And the scope introduced is for the parameters. These nodes will also update the scope field, so there's a field in this class, to track the current scope. So basically, nodes that introduce a new scope, they need to have this scope attribute set to an instance of that scope. Remember, it's this class here. Every type node, so that's a node for types. So for instance, that would be a type node, this would be a type node, etc. Mostly used int here. This is also a type node. And those need to have their value attribute set to the type instance. And okay, next, every return node, block node, and if node must have their returns attribute set to a boolean that indicates whether the execution of the node causes unconditional exit from the surrounding function or main script. So basically, a return statement will have the returns attribute set to true because it returns. If a block contains a return statement, unconditional, it will be set to true. And for if node, that's if both branches of the if returns, then the whole thing will be set as returns. This is used to check that a function that should return value do indeed return values. We also check a bunch of type constraints. So if we call a function, then we check that the parameters match the arguments that are given. We match that variable declaration have initializers that are the correct type, things like that. There's other things that we check. We check that if we access a struct, that the field exists, and that the variables are declared before being used, etc. Okay, quite a few things to do. So let's go into this class. There's a few fields here. So the reactor, you'll remember from my introduction, that is the thing responsible from orchestrating everything. And this will be aware of all the rules and all the attributes that we are computing. So the scope, that's the current scope that we're currently in. What do I mean by currently? Well, we're going to walk the AST. Okay, and we're going to do that in a depth-first manner. So we're going to start by the root, and then we're going to go to its first child, and then we're going to the first child of first child, and the second child of the first child, etc. Right? So we go depth first. We actually visit the top of the tree before going to the bottom. The inference context, it's a node used for inference. Currently, it's only used to infer the type of empty arrays. So for this, and I will explain this when we get to it. And the argument index is the function argument number that's also used for the same thing. We'll see that later. So you create this class by passing it just a reactor, and the entry point is actually here, so this is a static function. And what this does is that it returns a walker. Okay, a walker is a class from my utility library, which I recommend that you use. When you call this function, nothing happens. It just registers all the visitors for different kind of nodes, and then it returns a walker. Okay, so first step, you call this function. It registers everything. Second step, now you have a walker, and you invoke it and you invoke the AST. What this will do is that it will not compute the attributes, not yet. It will register all the rules. That's what the visitor does. The visitor registers all the rules. And then third, you use the reactor, the one that you passed here, and then you execute the reactor, and that's what will compute all the attributes. Okay. I have an example here actually. So this takes the file that you've seen earlier, it parses it, and then we get here. So we get the AST. Okay. So the language is called Psi, by the way. And so the top of the hierarchy is the Psi node. We create a new reactor. We create the walker by passing the reactor. So this just registers things in the walker. Then we actually walk the tree. And then now finally we're ready to run the reactor and compute the attributes. Okay. Oh, I forgot to print here. Let's remove that. So now we check that if there's any errors, and if there's error, we report them. And otherwise, we go to the interpreter and we actually run the thing. So what do we do in this create walker class? We create the walker and we create it, and here I use a reflective field walker. So that's also from my utility library. And we can check the documentation. This might be a bit small, but it says implementation of walker where the children of a node of type T are taken to be all accessible fields of the node whose value are assignable to T or are instances of collection parameterized with type T. That's quite a mouthful. What does that mean? So it means it uses reflection to know how to visit the tree. So if I take a node here, let me take a function call node, you can see that this has two fields. One is an expression node, and ultimately there's a Psi node also. And this is a list of expression node, and that's a collection of Psi node. Because expression node is a Psi node. Okay. Because of that, the walker is going to know that when it visits a fun call node, it needs to visit, after visiting that node, it needs to visit its children, which are the function and then all the arguments. It does that automatically. We also tell him that we want pre-visit and post-visit. What does that mean? Pre-visit means we want to visit the parent node before visiting the children. And post-visit means we also want to visit the parent after visiting the children. Mostly we're going to use the pre-visit, but in some cases we want the post-visit, and we'll see. So here we just create an instance of the class. And we need this instance to get the visitors. We are going to be methods. Basically, we have one method for each type of node. We're going to keep it very simple. And so for every type of node expressions, we have one method. It's all pre-visit. These are the nodes for type expressions. Here are the nodes for declarations and for scopes. And you can see here we use post visits. And these are the three kinds of node that implement or that introduce a scope. Okay, and what we need to do is that after we visit them, we need to pop the scope. So basically what happens is that in the pre-visit, okay, we can go there, we assign the scope. In this case, it's the root scope. And in the post-visit, we just pop the scope, which is to say we reset the scope to its parent. So that's very simple. I will maybe show you the block node here. Because in this case, we say that the scope is a new scope and the parent is actually the current scope. So we create a new scope whose parent was a previous scope. And then when we exit, we reset the scope to the parent. Okay, and then we have a bunch of statements. Expression statements, that's when you say you want to call a function, but you don't use the return value. That's an expression statement. We don't need to do anything for that, because we can just treat the function call expression, and so we just have a function that does nothing there. We also need to specify all of the actions for every node. Okay, so we said we want pre-visit and post-visit, but we only specified post-visit for 3 nodes. And so to make the framework happy, to make the worker happy, we need to say that there's a fallback. If there's no definition of post-visit, just do this function, which does nothing. And that's your worker. I've registered all the functions. So now we will go over all these functions, and we'll see what they do. So remember, these functions are run when the worker is being run. So when we traverse the AST. Okay. So in the test here, this is this step. So expressions. Let's start with something very simple. Integer literal, floating literal, and string literals. We know immediately what type they are. Okay. And so we do not need rules to compute them. And so we use big R here, that's the reactor, to say what is a primitive attribute. It's a primitive fact, we know it immediately. So we say that the type attribute of the node is int, or float, or string. Minimize this so we know where we are. So references, I told you references were references to variable and to function for function calls. So the first thing we do is we capture the current scope, and then we try to look up immediately. This is actually slightly tricky. So we try to do a lookup while we're walking the tree. And the reason we do that is for variables, because variables have a constraint that they need to be declared before they can be used. This makes sense. And so because of how we traverse the tree, we know that if the variable was declared before being used, then it has already been registered in the scope. But remember, a reference is not necessarily a variable. So we try to do this lookup, and when we get maybe context. Why maybe? Because if it does not find anything, this will be null. But if it does find something, if it's not null, then we can set the declaration on the node to be the found declaration, and we can set the scope to be the found scope. So that's very simple. And then we can create a rule. This is the first rule. With this reactor, we say create a rule. This rule will compute the type attribute on the node. So that's what's being computed. And using here tells us what it needs. So it needs one attribute, and that's the type attribute of the declaration. So for each declaration, we'll compute what's type. Okay, so for a variable declaration, the type will be the type of variable. For a function declaration, with parameter types and a return type. By tells us how we do the computation, and here it's very simple. We just want to copy this attribute into this attribute, okay? And this comes up often, so there's a shortcut for it. It's a method reference. It's called copy first because it copies the first dependency into the first exported attribute. And if the lookup succeeded, then we don't need to do anything else, and that's it, and we'll return. However, if the lookup did not succeed, then we need to create another rule. This will compute the declaration and the scope of the node. So remember, those are those things that we set there. And so in this case, we also have a by, but it's much bigger. And this small r there, this is an instance of, oh, that's not happy. It's an instance of a rule, okay? Air rule, you can see that's true. And the rule is used to read the dependency attributes, and it is used to write the supplied attribute, the exported attributes. This rule here computes 2 attributes. Okay, there are 2 exported attributes, and there are 0 dependency attribute because there's no using here. Okay, we directly go to by. So what do we do? And oh, something very important here. This whole thing here it's a lambda function, and it's not run when we walk the AST. This will be run when the reactor runs, okay? So at this point, when we walk the tree, we are only going to register the rule. We're going to tell the reactor, okay, here's a rule, so that you can, when you have those, when you need those things, you can run this, and we'll derive those things. But it's not being run when we walk the tree. So that's a very important distinction. What's in functions is run when we walk the tree. What's in the by function here is only being run by Uranium when we actually compute the attributes. So what do we do here? We again attempt the lookup, so the same thing we did here, except this time we're not walking the tree. So we finished walking the tree, so we know that we've registered every single variable and functions and every etc. We've walked everything at this point. And so this should succeed. If it does not succeed, if this thing is null, then it's an error. And so we can talk about error handling a little bit. The way it works is that basically the reactor keeps tracks of the errors. And errors can be set as the value for an attribute. Okay, if we cannot compute an attribute, we'll set this value to an error, and then the reactor will be aware of that. It will also be able to trace dependencies, because if we can't compute an attribute because there was an error, then all the other attributes that depend on that will also become errors. And the reactor will be able to chain all of that together to know that, oh, this failed because this failed. It can keep the causality. And this is helpful when it reports things, because then it can distinguish what's the root cause of issues and not give you 1,000 errors when really there was just one error at the root of everything. There are a few error reporting functions. This one is error 4. Okay, so let's go through the arguments. There's first a string, that's the error message. So in this case, I could not resolve the name of the reference. Then the second parameter is a location, which is a node. So location is always a node. This helps the framework tell you exactly where the issue occurred. And finally, we have a variadic parameter, and this tells all the attributes that could not be computed. Because sometimes, a rule computes multiple things, and sometimes an error just prevents some of these things from being computed, but not all of them. And sometimes it's more than all of them. Okay, so here we have 2 exported attributes, but this actually prevents 3 attributes from being computed. So the decal, the scope, and the type. We'll see why. In the case where it only precludes all these things, all of them, and nothing more, but also nothing less, then you can use another form. You can use just error. Okay, and for error, you don't need to specify all these things. So you could do this, and this would be fine. But because we need type, then we need to use error 4. So if it didn't fail, then we do set the scope and the declaration. Okay, and for this we use the set function. And we just say what we set. So we set the scope, the scope attribute and the node. And now we need to check what kind of declaration we're dealing with. Okay, so if we found a declaration and it's a variable declaration, well, we have a problem. Because remember, we said that variables need to be declared before they can be used. If it was declared before use, then this would have worked, and we would not have needed to define this rule. So if we're here, if it's a variable declaration, this is wrong, and we report an error to say that the variable was used before it was declared. So this blocks the computation of only the type attribute. Otherwise, we create a new rule. And this is interesting because we are in a rule, and you can see that within a rule, you can create a new rule. The reason is sometimes you need to create rules, and these rules will have dependencies, typically the dependency, that you do not know yet. So actually the result of one rule, okay, so when this gets executed, we get this information, and this information is in turn used to define further dependencies for another rule. So this is something that you can do. Be aware that you can do it, and you probably will have to do it at some point. And then the rule is very simple. So it's again copy first. So the type of declaration is the type of the node. Okay, so if the declaration was a function declaration, say with type with no parameters and return time string, then the type of the node, the type of the reference would be function with no parameter and type string. I'm talking about the type of the function, not the type of the function call. Okay, so to explain this difference, say we have the call here to validate 5. What you are typing now is not the whole thing. Okay? It's not the function. The function call is simply the reference to the function. So this thing here, that is as a function type. This whole thing here, that will have a type that will be the return type of the function actually. So it's different. But we type this thing, the reference to the function separately. Okay, another detail I should have drawn your attention to is that there's two ways to express attributes. So the function can take two parameters, the name of the attribute and the node, or you can pass instead the attribute construction like this, node.attribute.name. And what this does basically, it just creates this attribute class, well, an instance of this attribute class, which is just a pair of a node and a name. Okay, it's all it is. And it's a bit ugly, so that's why when there's only one attribute, there's a form where you can just pass those two things as separate arguments. But really what it does is that it always creates an attribute, okay, immediately. And you can always replace this by this form, and it's equivalent, okay, always. Ooh, that was difficult. Not an easy one, references. But you should be much more aware of what's going on. Constructor, this touches on structures, and I'm not going to do this in this video, so we're gonna skip that one. Array literal. This is another difficult one. Do we want to go into it right now? I will also do that later. Okay, we'll do some more easy stuff first. Parenthesized. So these are expressions in parentheses. This is trivial. The type of the parenthesized expression is the type of the expression within the parentheses. And you just copy that type over there. Very simple. What about field access? Field access has to do with structures, so let's skip that as well. Array access. Okay, this one we will do. So we define a rule, and this rule computes nothing. Okay, there's no exported attribute, but there is one imported attribute, and that's the type of the index. And what we do basically is that we check that it's an integer, and if it's not an integer, we report an error for it. So something interesting, you'll note that I check types using instance of. I could have done it differently because all my types, well, most of them, are defined as a singleton. So I could have compared with singleton, and I could have done this. I choose to use instance of here because I wasn't sure how it was gonna work. Doesn't really matter. Not something you want to waste time thinking about, at least at first. Okay, so this is a rule that checks the index. Then there's a second rule, and this is a rule that will determine the type of the array access. And for that, you want to get the type of the array part. Okay, so if you're typing xy, this is the index part, and this is the array part, and the type of this, well, it will just be the component type of the array x. So, okay, here we use the function get, and get is something that reads the dependency. We use get, we'll use it here also. So get, there's two forms of get. There's index-based. So index-based, you take the array here of dependencies, and you get them in order. So where there's only one, it's going to be 0. You can also specify explicitly what you want. Okay, so instead of saying error get 0, I could have said node.array type, because that's the first one, and that would have been the same. Typically, when there's just one, we will use the index because it's simpler. So we check if the type is an instance of, if it's an array type. If the array part is not an array type, then it's an error. You know, like if I'm trying to do this, for instance, this is not well typed, but it is syntactically correct because we have an expression and then I use an array index on it. So the parser will allow it, but the semantic analysis will reject it. Remember my advice from before, allow a lot in the parser, because in the semantic analysis, then you can make a good error message. Well, that's it, okay? If the type of the array part is not good, then we report the error that says try to index in non-array expression, and then we actually give the type of that expression. And if it's an array type, then we use the set, and then the principle here is the same, so it's index based, so we're going to set the type of the first thing, which is also the only one. And so the type of that is the component type of the array. So far, so good. Okay, function calls, that's a biggie. So this is used for inference, and I want to talk about it right now for empty arrays. But let's talk about this. So the first thing we need to do is to compute the dependencies for the rules. So what are the dependencies to compute the type of a function call? Well, it's the type of the function itself, and it's the type of all the parameters. So we do that. We create this array as big as the number of arguments plus 1. The first item is going to be the type attribute for the function, and then we are going to iterate over the arguments, and we are going to just put them into that array. So we know that arguments get the I argument and the attribute type of that. This is also a function from my utility library, but you could just do an old ugly Java loop. So this is the same as this. Is just that here you get the nice variable, and here you would have to write note that arguments dot get y. Actually, you see, I rewrote this, and I did not use it. There we go, much better. Okay, so we have dependencies. We can create the rule. We get the type of the function, and I say maybe function type because, again, syntactically something like this would have been correct, but now we verified that actually the type of the function part is a function type. Otherwise, we create an error. So we cast that to correct type. We actually already we can set the return type, because no matter what, the return type of a function call, well, the type of function call is the return type of the function. So we already do that. But now we are going to check the parameters. Okay, so we get all the type of the parameters, we get all the arguments. We check that we give as many arguments as there are parameters. And here I got a little bit fancy. I said, well, even if there's a different number of them, I'm still gonna check those that were given. Okay, so even if you give too much, too little, I'm computing the minimum between the two lists, and I'm gonna check those as well. So we have a boring old loop here. We get the type of the argument. So the nomenclature I'm using is that parameter is a type that appears in the signature. Okay, so A and B here, those are parameters. And arguments, those are the thing that you pass to the function. Okay, so result and AI here, those are arguments. So this argument matches this parameter, this argument matches this parameter. So I get these types, I compare them using the function isAssignable_to. And what that does is that it tells you if you can put basically a value of type A into a variable of type B. And so we can go through it rapidly. If it's void type, it's not compatible with anything. Integer types can be put into float types. If this type is an array type, then the second type better be also an array type, and their component type have to be compatible. So the A component type to be assignable to the B component type. Otherwise, they are also compatible if they're the same. And they're also compatible if the first one is null and the second one is a reference type. Like I told you, you can assign null to any reference type. So if they're not assignable, so if they're not compatible, then we also have an error. So finally, we have unary expressions. And currently, I only have a single unary expression, that's the Boolean negation. Okay, but it's written to accommodate more unary operators if I need them in the future. This is an enum, and it simply has a single member at the moment. So if we see this operator, well, we already know the type of the expressions, right? Because if you put not, then it means the type is a Boolean. So we actually set the type of the node to Boolean. But we also want to check that the operand of the not operator is a Boolean, because it only works in Boolean. And so that's what we do here. We want the type of the operand. If it's not a Boolean, then we create an error. Oh, sorry. So we have binary expressions. This is long and scary because there's a lot of combinations to take care of. Okay. I want to go through it very quickly. I don't want to do the details because it's quite boring, honestly. There's a lot of code, but it's boring. So if it's add, and if one of those is a string, then the result will be a string. So this is like in Java, you know. You have a string and you just press one, while the result will be this string. Then we have arithmetic operator, binary comparison operators. So those are your greater than, lesser than, binary logic, and then or, and binary equality. Those are equal and not equal. And so I have function to check which operators are what. For binary arithmetic, I check that int can be converted to float, things like this. And if you do arithmetic on things that are not int and float, you will get an error. The same for comparison. These have to be on number types. For equality, we actually have another function called isComparable. References are always comparable, and numbers are comparable, and void is comparable with nothing. Binary logic, we check that things are booleans. For assignment, we check that the left part is something that can be assigned. Okay, we check that the left part is a node that can be assigned, so it's either a reference node, so that would be a variable, a field access node, so that would be a field, a structure, or an array access node, which you write an array with that. And we can see that the type of the assignment is simply the type of the right-hand side. Okay, so there's left-hand side, right-hand side. And we are going to stay here for this video. So we've seen everything that has to do with typing expressions already, except for arrays and structures. I think I will do array literal. That way we are really done with things not related to structures. So there's two parts really to the array code, and the first part happens here in this if the component size is 0. And that's because when you have an array like this, you cannot say what's the type of the array. Okay, is it an int array? Is it a string array? You don't know. And so to find out, you need to know the context in which this occurs. And for this, we are going to read this inference context, okay? And this will be set by, basically there are two contexts that exist. And those are variable declarations. So if I write var x is an int array, then this node, this assignment node, will be the inference context. The other possibility will be a function call. If I have my function and I call it like this, then this function call will be the inference context. And we actually see the two possibilities here. So if the context is a variable declaration node, then it's very easy. We set the type hint to the type of the variable with copy first. Otherwise, if that's not the case, then what we do is that we also want to set the type hint attribute, but this time we need the type attribute of the function. Okay, so this is the function part of the call. And we also need the index attribute of the node. And this is something that we do in the function call, actually. We do set this attribute. And so once we have those things, we can just say that the type of the empty array is the type of the parameter that has the same index as this thing. Okay, so we get the function type, we access the parameter types, and then we get error 1. No, it's this thing, it's the index. And then we copy the type into type. This is actually stupid, okay, because we're just computing this, then we're copying it. We don't need to do that. We can just do this and then delete that. Right. This is what happens when you code at 3 AM. And that's for empty arrays. For non-empty arrays, what will happen is that we compute the dependencies, and basically those are the type of every item in the array. Okay, so it will be, we have 1, 2, 3, that will be the type of 1, type of 2, type of 3. And okay, just stream over the components, map them to their type attributes, put that into an array. Use that in the rule here. Then what do? Go from, we iterate on the indexes from 0 to the number of dependencies, and we get basically the values. So we get all the values of dependencies, and those values are types, okay? They're types of the items of the array. But we do not want duplicate types, so we use distinct here, the stream function that removes duplicates. Once that we have that, we're going to do a computation where we compute the most general type of all these items. I'm going to call it the super type. At the start, it's null. If we find a void type in this array, we report an error. But actually, so we could just abort there and say, oh, I'm not going to be able to compute the type of the array. But what I prefer doing is reporting the error, but still compute the type for the array using the other elements. Okay. So if it's the first type that I see, because super type is null, so the first type, I just assign it. And if I already saw a super type, then I use this function, common super type. And so the common super type will fail if there's a void type. Otherwise, if A is assignable to B, then B must be more general, or they're the same. Otherwise, we try the other way around. Is B assignable to A, then A is more general. Otherwise, they are not comparable or assignable in any way, and then we return no. So if indeed they are not comparable, then that means that they are incompatible elements in the array, and we could not find a common supertype for the array later on. Otherwise, we continue. If at the end we have a null supertype, that's because it's never been assigned, so it's never been here. If it was here, it would have been returned. But also it's not empty, okay, because otherwise it would have been handled there. So that means that this array only has void elements. So we just make an error that says, oh, there's only void elements. Otherwise, congratulations, we found the type and we just set that. And that's it for arrays, and that's it for typing expressions. And I will see you next time. Take care and enjoy life.